Our next speaker is Alex Marco, the director of the Science of Microscopy Center. What is your favorite part of the tomography workflow or instrument?
My favorite part?
Or instrument if you want.
I don't think I have one. Yes. Definitely not the processing. because it's too scattered at the moment. So I don't know. I mean, anywhere from after sample prep, microscopes.
Microscope. The first two speakers said FIBs, so this is very appropriate.
Cool.
Let's enjoy it.
All right, thanks. So, all right. Quick question: does anybody here have experience with FIBs? Okay, I'm a minority. Okay, cool. Otherwise, I would have done a different talk. This is how a FIB looks like, or at least this is my old FIB. Besides having eyes and a face, so you have a top down. You have an SEM column. You know, it's typically used just to look at the sample. At least in biology, this is all we do. You get sample topography, so you can see that what the surface looks like. At a certain angle, that can be pretty much anywhere between 45 and 90 degrees, depending on the brand and the model. You have an ion column. So the main difference between what happens when ions and electrons hit the sample is that because ions have a significant mass and a very short scattering cross section, what happens is that as they impinge on this is very slow. As they impinge on the surface, they actually sputter away atoms from the surface. So what you do is you're changing the topography of your sample as you're imaging. If you park your beam somewhere for a little longer, or if you have a little bit higher current, you actually dig holes. So you can look at this as any scanning microscope. The only difference is that every time you expose your sample, you're actually modifying your sample. Okay, so this is quite important because you need to be careful as you're imaging your biological samples, which are inherently very fragile. The other thing that you have to learn about FIBs is that everything is slow. There's a beater there because the amount of time you're waiting to the next section or whatever action is always very long. Beers are not allowed in the lab here. They were allowed in Germany when I took this picture, but I'm not sure they are allowed anymore. I think the world is going in a weird direction now. But, generally speaking, you have a lot of time to wait. You have, there's always dead time basically. So automation is something that kicked in over time. We'll talk about that later. So now, what are the different sources that you can have? And historically, this is the first source that was generated. So it's called liquid metal ion source. The way it works is fairly simple. You have a tungsten filament. You have very little tip here. And you have a reservoir of some kind of metal that is liquid at the temperature that is operated. So basically, you apply an electrical field. This will start sputtering away ions from the liquid metal from the tip, where the electrical field is the highest. And these will be then extracted, applied by applying voltage, and then accelerated and focused on the sample. So here, your source is this point. The timing. The smaller the point, the smaller the source, the higher the resolution. There's generally speaking one problem. As you increase your current, you start sputtering ions from further away. So your source is not going to be any more point, will be something that will resemble the shape of your tip. And this will essentially result into one thing, which is a loss of coherence. And the loss of coherence will result in a significant loss in resolution. So your spot size, as you increase your current, just goes up. The other alternative is a plasma source. This came out originally. I mean, the first one was introduced somewhere around 2005. And now more recently, the number of ions that you can use has increased. So the way this works is quite simple. Actually, you have a leaky vacuum chamber, you leak in a defined gas, you apply a radio frequency. This will essentially light up the atoms in here. They will all be ionized. You'll have a plasma glowing in here. The same as happening in your glow discharge and then you will have an orifice. This orifice will be your source. And then as you apply a voltage to extract the ions and to accelerate them and then focus them down on the beam, this remains your source. The advantage here is that it doesn't matter how much you crank up the current, the source size is defined. It will not change because it's an orifice. So you will crank up the current up to the point that as many ions can cross that orifice. And if you lower the extraction, you will have still a spot size of the same size. So realistically, the advantage of doing this is that as you are, if you're milling something with gallium, or if you're preparing a sample with gallium, this is an example where diamond was prepared. You're always going to be leaving some ions behind, and you will be seeing them because gallium, for example, is a very heavy atom. So you will see the implantation. You can see this bright spot. These bright spots are gallium atoms. If you were to use a very light element, or if you were to use an element that is sort of is gaseous and can simply move out from the sample as the sample goes into vacuum, then you will not be seeing those. You'll be able to optimize the chemistry of your beam for your sample and everything else that comes with it. So generally speaking, you can mill faster and you can mill better. But what's important here, and this is pretty much the only reason why plasma FIBs actually have become a major player more recently, is that your spot size does not get significantly worse as you're increasing your current. So what you're seeing here is the current density. So it's how many ions per micrometer square you can charge. You can see that in a liquid metal ion source, you have an optimum, which is somewhere here in the low nanoamp range. And as you're increasing, your density drops dramatically. If you have a plasma FIB, it will not be optimal in the lower end because your source is very large, your orifice is very big, but then the current density kind of improves up to a point where it stays fairly stable, and it will stay stable up to multiple tens of nanoamps, if not hundreds, which essentially means that you can mill faster because you have many ions in a very small spot size. Now, what do we use FIBs for? We dig holes, pretty much. So these are examples pretty much all done on silicon or diamond. I don't quite remember because when we took this picture, it was 2017 or so. You can make, if you have plasma FIBs, you can make microwave devices. Or generally speaking, it was all developed around the semiconductor industry, so it's all optimized for silicon. Everything you do in silicon with FIBs is fantastic. Any other material, pretty much an adaptation. Other things you can do is surface modification. So realistically, as you're irradiating, as you're imaging, you can actually modify your surface. For example, here, if you're exposing a silicon sample with xenon, you're just exposing to xenon and you're irradiating with some oxygen present in your vacuum chamber, what you will be doing is that you will be modifying your surface, and silicon will become silicon oxide, and silicon oxide then cannot be etched in case of exposure to fluorine. This is just to say, anytime you are exposing your sample to the focused ion beam, you are modifying your sample. You're not only milling it, but you are actually modifying the chemistry. Another thing you can do is, since you can define how much you're scanning, you can be very, very precise in tuning how much you're exposing. So this is a grating that we made on diamond, but what I'm trying to point out here is that we could actually make a very precise profile. So this is a cross section on the side of the grating. You can see that this one has parabolic profile. So the size, as you can see, this is about 5 microns. So you can be precise in the depth that you're milling in your sample, or you can control very, very nicely the depth you're milling in your sample. So this is good because it's essentially directly proportional to how much you're exposed, how long you're exposing each location in your sample. So you can predict this very nicely. Now, let's talk about damage for a second. I'll just go very quickly. There's a few things in biology we cannot do very easily, but material scientists can do much simpler. So when you when you expose your sample, as we said, we're modifying it. So one thing that you want to know is how deep is this modification going to affect your sample. So for material scientists, this is something very simple to solve and to measure. So I'll show you how they do it, and then we'll go into how we attempted to do it. So you have a sample in its original state, and you're going to go and polish a face. Okay, that's the green bit that's on the top. Typically, you put some platinum or some heavy metal that's very hard on the top, so to protect it. So you can polish this face, and this is going to be the face that you are interested in observing later. Then what you will be doing is that you will be adding another cap of some material that is hard, and then what you will be doing is that you'll be thinning that block from the other side. So you'll be making a cross section of a cross section. Okay, and at that point, you'll thin it enough that you have a sample that's ready for TEM, and then you can image this sample. So you will have a situation here where this is the area that you exposed to the beam when you polished. Here is the bulk that was never exposed, and here is the two yellow bits are the parts of the sample that are essentially the cups that you used for covering. And when you take an image, you will be looking at that area at the edge between the new cap and the bulk sample, and you're going to see how much has my beam damaged my sample. Okay. Now, just to give you a very brief, and sort of an edge case, if you're milling diamond is just carbon, it's perfect crystal. If you mill it with gallium, you'll have a virtually invisible damage layer. You'll have the little spots of gallium here and there that will be visible, but the damage layer will be virtually invisible. Using oxygen, you'll see no spots, but your damage layer is thick, which is great because it's over 10 nanometers, which in diamond is it's more than you can actually image, because if you make a lamella that is more than 10 nanometers thick, you don't see through. So it's something to be considered. Damage is something to be considered. The effect that ions have on damage depend on a number of things, including the sample itself and how big is the incoming ion. So, for example, this is BFO. This is a two-dimensional material that's used in solar cells, and if you're using xenon, which is very heavy, bulky atom, you will have a damage layer which will be in the order of one line of atoms, pretty much. It's 0.2 nanometers. If you are using argon for the same thing, argon is a much lighter atom. You see that the damage layer is about double. Okay, so lighter ions will always damage your sample more. That being said, there are advantages in using lighter atoms. We'll get to it. It will amorphize it more. Okay. Now, before I get into it again, it's like when do we use FIBs? So these are the samples that we are interested in biology, right? So viruses, we generally don't use FIBs for them because they're small, unless viruses are included in something bigger, like they're infecting bacteria, they're infecting cells or tissues. So you typically start using FIBs from anything that is thicker than half a micron. So that's the general idea. Up to half a micron, you can get away with your regular tomography. 300 nanometers probably considered the upper limit for high resolution, but you can get away with a little thicker. Anywhere above that, you're going to have to either do sectioning or use a FIB. There's not really any alternative there. The problem is that as your sample gets bigger, the complexity of your workflow, generally speaking, increases. And not only is the complexity of the data interpretation down the track, which is going to increase because you will be seeing a random section through your tissue, and you're gonna have to figure out where the hell you are. In life science, we essentially do two things. We do FIB-cell tomography. So in this case, basically what you do is that you dig a hole, you have a block face, and you're going to be imaging that, and you're going to be milling again, imaging, maybe image, and receive at the end of the session a large falling back. The alternative is cryo preparation, where basically you have your cell, which is too thick to be imaged with a TEM or your sample, and then you can make, you can thin down a little slab of material so that it's compatible with TEM imaging. This can be done in situ, or it can be done in could take out a piece of material and then thin it. That's called lift out. But generally speaking, it's one of these two uses. We're not doing anything else. In material science or in semiconductors, you can use it to, build structures. You can dig holes so that you can make surface. There's a ton of stuff. There's some guy in Spain that made springs, which were tiny springs. But you can make all this stuff. I think Theo, you come from that lab. So generally speaking, the sample preparation and the sample, like what you're going to do is going to depend by the sample and the answer you want to have out of it. And if you're doing three-dimensional imaging in any kind, so when it comes to FIB-cell tomography in general, you're looking at anywhere between 5 and 20 nanometers resolution. It can even be 50 if you're doing it at cryogenic temperature. So cryofib, actually, I said FIB workflows are all the same. It's partly true. Cryofib workflows are kind of all the same, really. If somebody tells you that they invented something else, they probably invented something that is already here. The steps are always the same. You're digging a big hole, then you're either preparing or not preparing your manipulator, and then you're turning around your sample, and then you're thinning down whatever sample remains around your big hole. That's it. There's nothing else really. You're milling trenches and you're thinning. Anything that happens in between is some kind of manipulation of your sample so that you can get your head around it and you can access it. But you can keep things very, very simple. So if you look at this, is cryo lift out or serial lift out, which has been probably the latest developments in the field. They are the more complicated. They use every component that it has to offer, from the focus iron to the manipulator, and even down and polishing. They're extracting the sample from where it was originated, and the cryo, all you're doing is you're essentially just polishing down your sample. You're starting from something that's already thin and you're just making a hole and polish it. The waffle is pretty much the same thing, but since your sample is a little bit thicker, what you want to do really is you dig some trenches so you can isolate it first, but then you just polishing it down. So you can see these are the spots, the points that are present or not in each of the workflows, but they're all the same. Once you learn to do one, you should be able to pretty much do all the others. Some years ago, we sort of introduced the automation on the FIB. This was to preserve our livers from drinking too much beer at the sessions. So we could do something else more constructive. But generally speaking, this is what you do. And again, every workflow is going to be the same. You're going to be doing a little bit more steps eventually, but it's going to boil down to these. You're going to select a region, and this is a region that shows some cells. And this is what you normally see on the focus ion beam. You're looking at it from at a certain angle, and that angle is going to be defined by what you want to do with it. You're going to see your perspective image, and you're going to decide, okay, that's where I want to do the cell, my lamella. And then what you do is, as I said before, you mill some trenches, you dig holes. Once you've gone through, you're going to realign, make sure that you are where you want, and then you're going to polish it. And you're going to end up with a very thin slab, which you can see here. On the projector, it's not super clear, but it's there. And if you look at it from the SEM, which comes at a different angle, you can see the surface. Okay. So at that point, you can you can take out the lamella and do some tomography. For example, this is sort of an example of a tomogram. we went from, the batch preparation helped a lot because we went from making 1 lamella per hour manually to, 4 to 6 lamellas an hour. There's still this feeling somewhere around the community that if you optimize and polish things manually, it's better. It's not, because you're not better than the computer, but it gives a lot of, the sense of control is still pervasive, I'd say. Most of the time, because it takes so much time to prepare the samples, you're better off increasing the number of, sites and lamellae that you're making, and then go back and take the ones that are good. Optimize maybe your workflow, your protocol, so that you maximize the number of lamellas that work, but don't spend time doing too much stuff manually because it's not well invested time. That being said, if you have a biopsy from a patient and that patient is dead and you cannot have a second biopsy, maybe you will want to be a little bit more careful, but generally speaking, go for numbers rather than perfect lamella. Now, if your sample is thicker, and when your sample is thicker is anytime you cannot just plunge freeze, okay? So anywhere you're looking at more than a monolayer of cells, your sample is going to be thicker. So something that was developed actually in this lab before I arrived is the preparation, what they called it, the waffle. So practically speaking, this is a situation where you have a sample that either is multiple layers of cells, or maybe it's a solution, cells are in solutions, or you could have proteins, you could have anything, just something that is thicker than 10 microns, I'd say. And then what you do is that you place it on the grid, which is down there. The grid is placed on a carrier that was previously polished, so that your sample will actually not stick to the carrier. And then you'll add that, and then you use a high pressure freezer to freeze. The idea is that if you go and did the previous talk about pressure freezing? Yeah. You know everything. So at high pressure, you don't need to freeze as fast, because the vitrification point is at -20 Celsius roughly. So you only need to drop the temperature very fast between room temperature and -20. The result is that you can have multiple layers of cells which are living on the grid, and then you can start isolating. So the isolation here happens, as I said before. You're milling trenches, you're isolating a region, and then what you do is you paint down the areas. And at the end of the day, you end up with a block of tissue and a very thin slab of material, which is electron transparent. That's it. If you were to do this for regular lamella, you would skip this. If this was thinner, you would just be making essentially the final lamella directly in low. Somebody last year came out with a different approach. I thought, how about we take something that is a tissue that can actually quite nicely self cryopreserve, and that's brain. Pretty much, that's the only one that I know of. Brain and yeast, because there's a lot of fat, there's a lot of sugar, and this basically acts as a cryoprotectant. They thought, okay, we can cut off a little bit piece of brain. This was actually from human brain. We can embed it in agarose, cut vibratome sections, which are in the order of a few tens of microns, and then we can just plant freeze it. The reality is this will not work with any other tissue, but they could make basically these vibratome sections here. You can see them. They are laid on the grid, and they could start preparing their samples for EM. The way to go for them was, okay, we have this sample here. Instead of lifting out or going any fancy, we're going to be basically just digging a trench at the back and then thin down from the front. So you can see it here. So all they did was they opened up at the back. They left a piece of material which they polished, and they ended up with many lamella one and two together. So this basically enabled some decent imaging. The sample is not great, to be completely frank. you have a lot of ice. You can see it here and there. On the other hand, generally speaking, the ultrastructure was not completely screwed up. So if you have a patient sample and you're working with with brain, or eventually if you were to work with yeast, it will work the same way because it's self-protecting. You can get away without high pressure freezing. But something somebody else came up with the fact that, well, maybe we need to high pressure freeze, and because most samples will not be self-cryoprotecting. So the idea here was essentially the same, and these are all variations of the same recipe again, right? I mean, you're taking a sample, you're putting it on the grid, and then you either plant freeze it or high pressure freeze it. And what they ended up with here is a bunch of essentially sections which were laid on the grid. They were pressure frozen, and then they could mill directly in situ. Yeah, you can see them up there. Some lamella, and this is how it looks like. The lamella are not great out of this paper, so their level of curtaining, so the unevenness of the surface is significant, and that reason is because they ended up using xenon among the various gases, and xenon is great because it's very fast. It does suffer from in order to make very polished lamella, you need to spend a lot of time. Curtains make your tomogram ugly. They do not make your tomogram unusable. So there's a little bit of a balance between how much time you want to spend on optimizing it, and how much time you want to invest of having a perfectly nice and sharp tomogram at the end. But you can see, nuclear memory is visible. Mitochondria look like mitochondria, and they looks like a wiggly tube, like it always does. So it's looking, the tomograph looked fine, the sample looks fine to me. Now, cryolamella preparation, if we want to go and explore, how do you actually, optimize it, and where do you optimize it? Most importantly, actually, let's start with this. This is your cell, right? Your cell is 20 plus microns thickness, and you go and decide that you want to pick something that's somewhere in that cell. So if you just shoot blindly, you probably miss it because you're taking 200 nanometers out of 20 microns, right? Or 10 microns, or however big. So you're doing this. I always put Waldo in my slides. One way or another, and it's cute. And we're doing cryo-EM, so everything's blurred. Nothing looks like what it should do. And then what you do is that you're going to pick anything that looks like a stripy thing, and you say, this is Waldo, right? And these are all the options. Some of them are more obvious than other, but the reality is that it would be easier if instead of picking randomly, you would have, Waldo would hold a torch or something. So this is pretty much what we're doing when we do correlative microscopy. So what you do is that you can do light microscopy. You can take your images here. These are some of these sections. So these are our sections of tissue. You could do it on plant frozen samples. It doesn't matter what your sample looks like. Everything is frozen. You just take pictures, and you know where whatever event of interest is located by light microscopy because you can tag it. And then the next thing you want to do is you want to correlate that image that you have. 3 minutes only. I'm like halfway. Okay, I'll go quick. You correlate quick, and you'll find yourself with with whatever object of interest within the slide. You can do this at higher resolution. Okay, if I could have spent half an hour on the Sophie, but I will not. Generally speaking, super res is cool, nice. It's only useful if you're trying to understand if something really, there's a bundle, is not a bundle, or some within a structure. Otherwise, it's really not particularly useful for us because we're going to go at much higher resolution later on. Just want to know if the structure of interest is located where you're imaging. You could do this in 3D. All these methods exist. You can use beads. You can use any sort of reference point that you see in both light microscopy and EM. And then you can take your images, and if you've done your work correctly, then you can identify the regions or the objects of interest that are present in your final tomogram at the end. This is all cool. The problem is that when you're doing this, most of the cases you have, you go from light microscopy to cryo-EM, you're doing 4 different sort of transfers, and this is what you end up with. If you're doing cryo-SEM, you'll see a lot of that. And they're ice crystals are beautiful, but they are a little bit of a problem. So we ended up doing this. This was years ago. You could do it in super resolution, we've done all this. Now, this day, what you should be doing is probably buy something off one of the companies because it is, it's faster. You just plug it in. It's kind of interesting that the latest and best on the market is as good as my first prototype, which was like 8 years ago. I don't understand that. But regardless, what you end up with is essentially a decent way of mapping your sample. You don't need to transfer, they work fine. It's just as it should be, pretty much as advertised. Both options actually really do that. Some softwares are better than others, but I'm not here to judge. Now, just back on the lamella prep, if we go, what I was mentioning earlier, some of the sources that you use, some of the ion sources you use, will have an effect on how good and how stable, how flat your lamellas will be. The lighter atoms will behave better than the heavier atoms when it comes to curtaining, but they will amorphize more. As I said before, lighter atoms will damage your sample metal. This is something that has to do with the final, the spread of the ions inside the sample. But generally speaking, these are 3 very different oxime beams, and they all generate perfectly usable tomograms. So you can use pretty much anything that's on the market. They will operate. In all cases, they will operate okay. Plasma FIBs will be better for thicker samples, generally speaking. If all you're looking at is cells on a grid, it doesn't matter what you're using. This is a reality. Now, this was, just to give you an idea about the damage. This is an ion impinges and then it scatters into the material, and how much it struggled inside the material. Yeah, I'm pretty much done. How much it struggles inside the material depends on the density of the material, the composition of the material, and how heavy the atom was. So when you make a 300 nanometers lamella, you really have about 220 which are usable. The rest is going to be just damaged, and that damage is not useless. It's a stochastic damage. So depending on the lightness, on the acceleration and how light your atom is, it really will. You may have a complete, will render it completely unusable. 30 kV oxygen will make it completely unusable, or it will be restricted to the surface. Somebody came up with a way to quantify this, and the stochastic damage quantification. I will skip on this, and I will go on to this, which is a paper that a bunch of people don't like, but I find it's very useful because it directly relates the damage to those damage you see with the TEM, with the electrons from the TEM. So it's the same as like your very edge looks the same as a little bit of a more exposed or later frames in your regular single particle stack, basically. What I mean here is that you'll be able to get to high resolution. You'll just need a lot more data. That's all. So if you're looking for high resolution, who cares? Just go use whatever ion. Doesn't matter. If you look for something very, very rare, maybe you're going to have to care about this. Now, this is again something else that has to do. Ion implantation does deal with signal to noise. You'll be losing some of the spots. The spots are clear; they're just less visible. When you're using gallium, it does have a little bit of that effect. And if you're drilling through big materials, you will probably want a focused ion beam that has a lot of current. So look at that compared to gallium. Now, I'm completely done, right? Supposed to. So I have to skip on lift out. Bum, bum. You're taking out lift, well, I can do this. When you're taking lift out, you start from something like that, then you start digging holes, and you'll end up with a piece of material that's completely isolated, and then you can thin it down, and then once it's thin, you can look at it in TEM. So now I'm gonna have to skip through this because I've been too slow. Lift out has a bit of a problem. It contaminates like hell. These posts here look like junk at the end of your transfers most of the time. So the guys in Martin's Rig came up with an idea. We should be using regular grids, and we could also deposit multiple slices throughout. This is actually, it turns out to be easier than a regular lift out, so it was a very good idea for many reasons. Somebody else from the same lab thought maybe we should deposit it on carbon. Excellent idea as well, because it makes things even easier, although you're wasting more sample. Generally speaking, you're basically getting context out of your final sample. Now, you're getting basically serial sections. You can take your TEM tomograms, and then you're going to have to struggle your way through the processing at that point. Just one thing that I wanted to live with, which is, and I know I shouldn't be saying this because I'm heading a cryo facility, but don't do cryo unless you really have to. Because if you are looking at a sample that looks like this, there's no way you can get that out of cryo. So do cryo only if you actually need resolution that goes sub 2 nanometers. Down to 2 nanometers, do plastic. Please do yourself a favor. You can get tons and tons of data, tons and tons of context. Just choose. I'm not saying don't do cryo in general, but choose your problem and choose your technique. Because a lot of people tend to go into cryo because it's cool, but then they get nothing out of 3 years of work. So maybe just pick your battles. If your sample cannot be changed, maybe stick to resin. There's nothing wrong with it. These were just examples of hundreds of micrometer cube of sample. Have I gone far too long?
Far too long, but it's good.